Hello, class. I have quite a good lecture for you today. It's on the summing amplifier and the difference amplifier using an operational amplifier. And I want to go through the actual analysis, the Kirchhoff's current law analysis on both the summing amplifier and in some ways, as far as the summing amplifier goes, it's very much an extension of the standard inverting amplifier, which I spoke about in our last lecture. And, I want to encourage you to go, when you're back on campus, or get a 741, buy a 741, start looking at it. And, I know that they're going to send breadboards and stuff out to you. Actually, the simulation, that you're working on for this class, they have op amps in there, and you could, I may even give you a lab so that you can do a simulation with an op amp. Anyway, let's get back to this. And you're probably wondering why I have the truth table here all the way up to 15 with the binary numbers, right? So I've got binary numbers out here, and we're going up to 15. So I'm going to look at a certain application of the summing amplifier. But first, let's go through the summing amplifier, and I've got quite a bit to teach you today, so I'm not going to, spend a lot of time, waste a lot of time with amusing anecdotes or anything. We've got quite a few things to do today. So with the summing amplifier, it's just like a inverting amplifier, right? If we have our so I'm just drawing it, just like an inverting amplifier, right? There's my output, V out. And I'm also going to have a feedback resistor, aren't I? So there's my feedback resistor, R sub F. And then I also have resistors here. Now, these resistors do not have to be the same value. So I'm going to call this R1, R2, and R3, right? I'm going to try to stick as much to the notation in your textbook as I possibly can. And if you look at the current flow that we've got here, I've got current that's flowing in from here. Now, I have to, put on here, this will be V, I can't draw power supplies for each one of this. This is going to be V in 1, and this is V in 2, and this is V in 3. So I've got 3 ins and I've got 1 out. So how's the current flowing from these voltages? Well, isn't the current flowing through R3 and then up here to the node and then through the feedback resistor and out the output, or connecting out to the output there? And then the same thing is true when we look at, I dropped a pen. When we look at the current that's flowing out of this one is going to flow up here. It's going to meet with that, then combine with that current and flow out, isn't it? And if we look at the third one, it's the same thing, except this is blue, but it really looks black. And that also flows out. Probably have to just use the black pen. So I've got all 3 of those currents. Let's call those currents I sub 1, I sub 2, I sub 3. So I sub 1 plus I sub 2 plus I sub 3 is going to equal I total. Right? I'm just calling it I total because that's the total current that's flowing through that feedback resistor and flowing out, right? So I don't think anybody's, I don't think I've lost anybody by doing that. But we want to look at these. These are all combined together, aren't they? What are those currents? Well, let's not forget that V equals IR. How could you forget when I write it down in almost every lecture? P equals VI, right? So always remember that. two great equations. Now, when we're looking at these, and we're looking at I1, so what is I1? I1 is just going to be the Vn, right, over R1. So Vn minus, let's call this, let's give this, let's call that A, that point right there. Does everybody see that? That point right there is A, just like we always call it A, right? V sub A, whatever. So I is going to be V1 minus VA, or Vn 1 minus VA. I'm going to regret putting that in there, aren't I? Divided by R1. And I sub 2 is going to be Vn 2 minus V sub A divided by R2. Like I say, they can all be different. I'll just drop a line down between these so we know that they're all different ones. I3 is just going to be Vn3 minus VA. And you know what VA is too, don't you? I think everybody who's, because we've already done this one time before, is going to say, well, if this is 0, right? If this is 0, V plus equals 0 volts, then I know that V inverted should equal 0 volts too, shouldn't it? So we know that VA is going to be, which equals VA, by the way, is going to be 0. And we can include that later on in our analysis. Right now, I'm not sure that we, really have to do that. What's I, by the way? Look at this. I, that's I total. So what is I total? Well, we can see it's going to be V sub A minus V sub O, so V sub A minus V out divided by that resistor right there, R feedback, right? Everybody see what I've done with all of these? And so really, let's put all of these now back into this equation, but let's use some analysis that tells us that V sub A is going to be equal to 0. Right, so we could rewrite all of these, and why don't I? I don't want to lose anybody, but basically what I'm saying is this is just going to 0, right? So VA is going to 0. Doesn't that make it just Vn1 over Rn1, Vn2 over Rn2, 0, Vn3 over Rn3? I really don't have to write all of those again, do I? So I get. I'm going to write this out twice, but I don't want to lose anybody. Minus V out over R sub F is going to equal V in 1 over R1 plus V in 2 over R2 plus V in 3 over R3, right? Can I simplify that? Absolutely. I can say that V out, right? The negative can come over to here, and the R sub F can go up into the numerator here, so that's minus R sub F over, let me see, what am I? Yeah, no, that's just R sub F, God, I don't know, I'll do it. Minus R sub F over R1 times V in 1. Well, I won't have enough room to write that all out. Let me write it down here. V out. I think everybody can see what that's going to turn into. I just wanted to, I could throw the negative. I'm not even going to throw the negative outside. R sub F over R1 times V in 1 minus R sub F over R2 V in 2 minus R sub F over R3 V in 3. Does everyone see how I'm going to circle that in red. Does everyone see how that all algebraically worked out? And basically what it's saying is when we have a summing amplifier, due to the fact that I've got no current that's flowing into the amp at all in the front end, we basically, with the summing amplifier, just are able to sum all of those voltages together. Now, I want to talk to you about a special application, and that's why I've got the binary table, truth table here, right? Actually, it's not a truth table, it's just a binary table. I counted up. You know, if you're counting up, this is a 4-bit binary table, right? 0, 0, 0 equals 0, 0, 0, 0, 1 equals 1. I think everybody knows that. And then 0, 0, 1, 0 equals 2. If you don't know how this table goes, memorize it very quickly. So you can see how I'm counting up in binary all the time, right? And these down here, this is 2 to the 0, and of course anything to the 0 is just the ones column, right? And then I've got the 2 to the 1, 2 to the 2 squared, 2 cubed, and we do that exactly the same way using base 10, but in this case we're just using 2 choices, a 0 or 1, right, as we go down. So this is how I would count up to 15 in binary. And you're gonna, if you're not taking that right now, you're gonna be taking it next semester. So start to learn your binary and how we would count in binary. You know, when I put this table together, here's how I do it. Since I know it's a 16, 16 different, I was gonna put the steps in here, and then I put the numbers in, and I thought, God, those steps, if I put the steps in here, it's gonna confuse people, right, as to what the value of this is. And so I crossed it out because I just want the value. 0 to 15. Isn't that 16 steps? That's right, 16 steps. You know, 16 steps, isn't that 2 to the 4? That's why we call it a 4-bit. 16 steps is 4 bits, right? Because I can use 4 bits to delineate the various different levels, the 16 different levels from 0 to 15. So there's 16 levels, but there's only 15 numbers, and you can figure the numbers out. Look at this, 8 plus 4, that's 12, plus 2, that's 14, plus 1, that's 15. See how that works? So totally different than anything we're doing with this class right now, but here's the summing amplifier I want you to look at. It's important enough that I'm going to take a little time now to show this to you. Even though, you know, that you're going to get this probably again, I don't know, you know, I'm sure you're going to get it in analog circuits, but, you know, even on your way there, you can do a lot of stuff before you ever get to analog circuits, right? So this is the 4-bit digital to analog converter. You've probably heard of a DAC. A DAC stands for digital to analog converter, right? And that's what this is right here. So let's say I put a 1 kilo ohm resistor right there. And I put a 1 kilo ohm resistor here. And then I've got a 2 kilo ohm, and I've got a 4 kilo ohm, and I've got an 8 kilo ohm. Right? Does everybody see that? Now, let's say that I was to say that a 1 equals 5 volts, and a 0 equals 0 volts. That's a 5. I don't make 5s too well, do I? Or 2s. Anyway, it's a 5 volts, and that's 0 volts. So let's see. Let's just pick a number, any number that I want here, but one of the ones that are up a little higher, maybe. What if I went with 15? What if I went with 15, 1, 1, 1, 1? Then wouldn't that be 5 volts, 5 volts, 5 volts, 5 volts? What would come out the other end if I put 5, 5, 5, 5 with that? Well, let's see. So we've got 5 volts, right? Times the negative R sub F, well, that'd be 1 to 1, because this is 1K, right? 1 to 1, so 1 to 1. So it's just going to be, so V out is going to be 1 to 1. I'll even write it out. Minus 1,000 ohms over 1,000 ohms times 5 volts. Does everyone see how that worked? Minus. I think everybody can see 1,000, 1,000, I cancel out. So that's just going to give me 5 volts there, isn't it? Now the next one is going to be minus. And then what's my, excuse me, I'm just going to put some parentheses in here. What's my feedback resistor? Well, that's 1,000 ohms. And what is my input resistor? Well, that's 2,000 ohms, isn't it? So it's 1/2 of 5 volts. So that's 2.5 volts. Let's do the next one. Minus, now these are minuses, of course, right? The next one is going to be minus, now I've got 1 kilo ohm divided by 4 kilo ohms. So 1,000 ohms over 4,000 ohms, right, times 5 volts. That's going to give me 1.25 volts, right? 1.25 volts minus, sorry, it's a minus, minus 1,000 ohms over 8,000 ohms, right? Times 5 volts. So that's going to give me minus 0.625 volts. Right, so everybody see their minuses. Don't worry about the fact that they're minuses. They're still, we're looking at the magnitude that's coming out of here. Right, so let's look at that. This is going to be 15. So it's going to be 15 times something. So 5 plus 2.5 plus 1.25 plus 0.0625 equals 8. Did I do that right? 5, 2.5. 7.5, 8.75. Yeah, no, something went wrong here. Just a second. Oh, I see what I did. 0.625 plus 1.25 plus 2.5 plus 5. 9.375. Does everybody see that? You know, you're probably saying, hey, isn't that the same as 10 minus 0.625 volts? Yes, that's very sharp of you. That is so sharp of you to see that when we do have this, we're up to 15. We never do get up to 10 volts, do we? No, because the full thing is only going up to 15. Now, that's an analog. What if, and this basically what we're saying, this binary string has just come into your audio player, right? It's being turned into a voltage so that you can hear it. Right? That's how we do it. We digitize audio signals. So let's say I've got an audio signal that looks like this, right? And what I do is I take slices of it. I sample that audio thing at various different places, right? I sample it so that I can find out what the voltage level is and lay that down in my digital track that I've got here. And then later on, when we're listening to music, it comes out digitally, and then it plays all of these notes, right, at this volume, right, as we go across there. So it recreates the music pattern that was the analog. That's what we listen to. When we listen to music, we're listening to an analog waveform that is changing the frequency of vibration of the baffle inside our speaker. Everybody get that? Okay. I didn't want to talk to, but that's what it's doing. All right, so this is this is what I've drawn right here is a stripped down 4-bit DAC. You know, you don't it's a great little DAC too, and I'm sure that you're going to put something like that together when you get into analog circuits. You'll be putting DACs together and ADACs. ADACs are, ADAC, by the way, ADC is an analog to digital converter, right? So just get your terminology and the nomenclature down. A DAC, digital to analog converter, and an ADC. Sometimes people actually spell it out. I call it an ADAC, but you know, people call it an ADC sometimes. Analog to digital converter, digital to analog converter. And that's what this is right here. It's a specific application of the summing amplifier. And it's great. It works so well because it's an active circuit, like I said. Now, I don't know if I'm going to have enough time to get through the full derivation of the difference amplifier, but I'm going to try. We'll see how it goes. I'm not going to draw it anywhere near like it looks like in your book. I'm going to call this V1 in, and that's just going to go through a resistor and then go into my op amp, right? And of course, yes, I do have a feedback resistor on the op amp on this side. I'm calling that V1. Now, I'm going to make another circuit. I'm going to make another circuit with V2. That also is going to go through a resistor there, but before it goes in, well, I shouldn't say before, at the same time that it goes in, there's going to be another pathway through resistance down to ground. Okay? Now, let me label these resistors. This is going to be R1. This will be R2. This will be R3. And this will be R4. All right? That is I'm going to, you know, oh, I got a big green one. Let's see if I can use it. Oh, look at that. That is your difference amplifier, and also comes in, you can use it as a subtractor amplifier too, or you can use it as a subtractor that is amplified. So this is your difference. Don't mistake a difference amplifier for a differential amplifier. They're two totally different things. Obviously, a difference amplifier talks about subtraction, and a differential amplifier is what you use inside the op amp. That's what the heart of the op amp is a differential amplifier. And what I really mean by that is something that uses several transistors. You'll get to that later. I'm not going to teach you what's going on inside the op amp right now. You'll get that later. I'm teaching you how to use the op amp in applications. And that's what your book really is doing too. It's just looking at a short analysis of how the op amp from outside, looking at the black box, works. And so I always love to give that to students. What I find is that even way before you get up to the other things, you're already building circuits in the lab using the 741 op amp. 741 is probably the most robust, and it's the common one that we use in lab, although there's op 177s and 170s, and there's a whole different variety of op amps that are amplifiers, active amplifiers for a whole variety of different high power op amps, low power op amps, sensor op amps. So there's a lot of op amps. I don't want to spend too much time on it. What I want to do now is I want to look at node A. So I'm going to call this node A. I'm going to call this, I better make a node B. I'll make them both red, but then I'll actually call it A. And if I can write small, I'll call that B. Does everybody see where A and B are, those two red dots? So the first thing that we want to do is we want to consider the currents flowing in to node A. And I'm going to point out, where did I lose it? No, there it is. I'm going to point out the same thing that we did before. We're going to analyze it very much. There's no current flowing into the op amp, right? So all of the current that's coming through here is going to flow through that feedback resistor and to the output. Right? Does everybody see that? So if I call this I1 up to that point, and I call this I2, well, we know I1 and I2 are the same, right? So we really don't have to worry about it because they're the same. So if I1 equals I2, that's what I'm just going to say. I1 equals I2, like I have, all over the place. Then we know that V1 minus V sub A, let me write this with, I don't want to use up all my green. V1 minus V sub A divided by R1 has got to equal V sub A minus V out divided by R2. Does everybody see that? I think that's pretty straightforward. And in fact, all of the analysis at node A is pretty straightforward. If I were to solve this for V out, let's just, I'll give you a couple steps. In the book, they really don't put the steps in. There's some intricate steps that you should understand in going from this point right here all to the way to the end of the difference amp. I'm going to try to put those in here, even if I have to go into the next lecture to make sure. And I don't think I will. I think I can get this out of the way. So let's just do a little algebra here. I don't want to lose you in the algebra. So if I am solving for V sub O, can I throw V sub O over on the other side, multiply this side by or get rid of this R2, put that over here. So I've got R2 over R1. And then I'll have VA minus V0, right? Can I take that V0 over to the other side, make it positive, and take all of this over to this side and make it negative? That's right, I can. So V out, and that may be two steps, but I think everybody can see what it is I'm doing is going to be V sub A minus R2 over R1 times V1 minus V sub A. All right. Now, I can expand that out too, can't I? So I could say that V out equals, I'm just going to expand this whole thing out, equals VA minus R2 over R1 V1 minus plus R2 over R1 VA. So V out, I've got VA, VA, so I can take VA out of both of those. So I'm going to have R2 over R1, right? And I've got a plus VA here too, plus 1. That's a 1. That's a parentheses. I can't win. Times V sub A. And then minus R2 over R1 times V1. All right, let's circle that because we're going to come back to, yes, I had to draw everything wrong there, but we're going to come back to that later on. And, excuse me, and solve the equation by substituting back in, components for V sub A. Anyway, that's the first part of this. I may not have enough room to totally finish this on the page, and we may have to do it next time, but let's just do, this is at A. So let's put that there. And then let's use the remaining room that I have to analyze node B. In fact, I should put, there you go, node A, right there. And then this next one is an analysis of node B, which is more difficult. Node B is, looking at node B, it becomes a little more difficult, but let's just get our equations anyway before I'm going to step into the next one. So looking at node B, I know that the current in node B, same thing. It flows here, doesn't flow into the op amp, and it flows down through here, right? So let's call that V sub B, right? Excuse me. So this will be V sub B. So I know, since that's all the same current, I3 is going to equal I4, right? I3 equals I4. So that's V2 minus V sub B divided by R3, right? And we know that is going to, that's a B. V2 minus V sub B over R3 is going to equal V sub B minus 0, I'll do that one, that's V sub B, over R4. All right, I have done a few. Now, what I want to do, I think everybody can see the V sub B minus 0 is just going to be V sub B over R4. So if I solve for V sub B is going to be R4 over R3 times V2 minus, wait a second, what have we got? Have I got to 2 V sub B? Yeah, no, I'll do it in, I'll do it in 2 steps. R sub 4 over R sub 3 times V2 minus VB. If I take the R sub 3 over R sub 4 times the minus R sub V over R sub 4 and bring that over to the other side, that's V sub B plus R sub 4 over R sub 3 times V sub B. So I'll have, a second, and that equals, yes. Yeah, we can do that. I think I have enough room. So anyway, should I expand that? No, I think everybody can see what I've got here. I'm just going to have V sub B plus R4 over R3 V sub B, right? It's a minus, so it comes over, it becomes a positive, and that's going to equal R4 over R3 V2. And of course, I can take V sub B out of that on the other side, which then leaves me with just 1 plus R sub 4 over R sub 3, right? And that equals R4 over R3 times V2. So if I wanted to, I could, well, no, that's you know, fine. I think I've sort of run out of any more room to expand on this, though, and I'm almost at the end of the 35 minutes that I usually set aside. But I just want to make sure, I'm just going to look at this to make sure that this is the same thing that I had there. Did I do that right? Let's see. VB R4 over R3 plus R4. V2. Well, I haven't really gotten there yet, but I've sort of run out of room to solve this for V sub B. I guess no, I don't think I can really finish that. I'm going to finish this up from this point forward on our next lecture, which is going to leave the difference. I was hoping I could get the summing, the DAC, and the difference all in time, but it looks, I've got 30 seconds left, and there's no way, and I've run out of room too. So we're going to finish this up. Finish next lecture. Well, there you go. You'll have something to wait for. So anyway, we're going to finish this up with a difference amp. We're going to do an example of using the difference amp. I want to bring out a couple things. You know, I would like to mention this, though, that what you're going to find for the difference amp in the end, once I finish this relatively long, there's a long derivation. Sorry, time's up. There's a long derivation, but what I'm going to end up finding is that R1 over R2 must equal R3 over R4. We're going to find that has to be a case with the difference amp. If you want the difference amp to work correctly, that's going to come out of our derivation. And then we're going to look at how we would, set this up and everything else. Okay. See you at the next lecture.